Okay, we're beginning chapter 7 today on atomic structure and periodicity. Um, we are going to be looking at atom behavior, first of all, from the classical mechanics sense, which um, treats waves of light or treats energy differently than it treats matter. Matter has one type of behavior, and energy has another type of behavior. Energy being wave-like, and matter being particle-like. And we're going to find that the, the classical mechanics model struggles to explain all the concepts that we are seeing happening with atomic structure. And so then we're going to move into the quantum mechanics model, which will blend the two together. Okay? But now, in order to understand atomic structure, we have to start out by studying light or electromagnetic radiation. So it's important that you keep some questions in the back of your mind as we talk about light. Like, why do we get different colors of fireworks? Why do we get different light colors? And why do different chemicals give us different colors when they're excited by energy? And so keep these questions in the back of your mind as we begin to talk through this whole atomic structure idea and how it relates to the periodic table and the repeating patterns that we see. Okay, so we're going to start out looking at the characteristics of light or electromagnetic radiation. And we know this is how energy travels through space. Okay, and so light or radiation has three distinct characteristics that help us explain or study the nature of light. And that is wavelength, frequency, and speed. Okay, and so wavelength uh, is defined, if we move on to the next slide, wavelength is defined as the distance between two consecutive points on the wave, whether you use the peaks or the troughs or the baseline. And we symbolize it with this symbol called lambda. Okay? And frequency is the number of waves that will pass by a specific point in space in a second, okay, in a unit of time, which we use seconds. And we use this little symbol for frequency. Don't get it mixed up with velocity. That's frequency, and that's called nu, okay, Nu. These are Greek symbols. Okay, and we're going to relate our wavelength and our frequency to the idea of speed. And so we know that light travels at the speed of 2.9979 times 10 to the 8th meters per second. We're going to use 3 instead of 2.99 because 3 is what's on the handout that you get when you take the exam. So 3 times 10 to the 8th is the value we're going to use. Okay, so now here is speed of light written as an equation with wavelength and frequency. And notice that wavelength and frequency have an inverse relationship to keep speed of light constant. Okay, so let's move on and examine those two relationships. So here's 3 different waves all drawn to represent a time of 1 second passing. And you can see that the top wave has this wavelength, okay? And then the second wave, the wavelength is much shorter, okay? And then the third wave, the wavelength is even shorter yet. And so as the wavelength gets shorter, notice that you can have more waves passing by in that second time frame. And so as the wavelength gets shorter, the frequency gets higher. Or as the wavelength gets longer, the frequency gets lower. And there's that inverse relationship. Okay? Now our units for frequency are what we call hertz. Okay, and that simply means the number of waves or the cycles per second that are happening. So you can take the frequency of anything, just whatever repeating pattern you have, whether it's a beat, okay, or a clap. It's however many cycles go by in a second time frame, okay, and we call that hertz. And then wavelength is measured in meters, And if the waves get really small, we tend to use nanometers to work with better numbers. Okay, so in the next slide, or after this slide, I'm going to insert a clip showing you how to use the speed of light equation. Okay, light or electromagnetic radiation can be put into categories so we can talk about it, because it's really all the same thing. It's a wavelength of energy with a specific frequency. So as you look at the spectrum, okay, notice down here on the left, we've titled this end, we've titled these gamma rays, and then X-rays, and then ultraviolet rays. And then we head across the visible light, and we see infrared, microwaves, radio waves. Okay. The waves on the left side of the visible light, these all tend to be ionizing radiation, meaning they can mutate cells and they can rip electrons off of atoms. Okay, so that's why when you go outside, you get a sunburn. Okay, that ultraviolet radiation is harming your skin. Or when you go to the dentist and they take X-rays, they put that lead jacket over your chest so that you protect your vital organs from getting this ionizing radiation. Okay, and then the infrared, microwaves, and radio waves, we call these non-ionizing radiation. Okay, now you might be thinking about microwaves and wondering, well, I know microwaves aren't good for me. And that's because the microwave causes water to resonate. They have the same frequency. And so when microwaves hit water molecules, the water molecules vibrate. And or resonate is another word for that. And then that's what causes the water to heat up. And so that's how we heat our food. And since we are mostly water, that's how we would heat up. And so that's why microwaves are not good for us either. Okay, so remember the inverse relationship. Okay, really small waves, so high frequency. Also high energy. Really short waves down here at the other end, really long waves at the other end, gives you low frequency and low energy. All right, we want to start to try and relate the idea of light and matter kind of having a similar relationship. And so here's an example of what we call the electric pickle or the pickle light. And what's happening is electricity is just being run through the pickle, and the sodium atoms in the pickle are being excited, and electrons are jumping energy levels. Okay, and they're releasing energy or photons of energy. They're releasing little bundles of light that we think are a continuous stream, but they aren't. So we'll be talking more about this pickle light idea in class, and we'll demonstrate this, and so we can address this idea more. Okay. Now, like I said before, the wave nature of energy was running into problems because some things couldn't be addressed. Some things like black body radiation or the photoelectric effect. And what happened is Max Planck started to realize that there is a relationship between light and matter. And he started to see that energy isn't released in a continuous stream. It's actually released in little chunks, little bundles, little packets he called photons. Okay? And he could actually put a value to them. And so that's where he came up with this formula, energy equals his constant that he determined by experimentation times frequency. And so this has a direct relationship. The greater the frequency, the greater the energy. And he was able to calculate that energy. And so he started to realize, look, energy is like matter. It's particle-like. Okay, and this is basically what I was talking about here, is that whole idea of is energy is quantized. It comes out in chunks, and we call them photons. Okay, and here's Planck's constant that he determined through experimentation, measuring energy and frequency. He was getting this same value, and so here's his constant. Okay, this is also on the green sheet in the AP exam, so it's not a number you have to memorize. But now we're looking at energy as acting like particles, like energy has waves. So it's kind of got this dual nature. Okay, so I'm going to insert a couple of example problems now so that you can see how this formula works with some of the practice problems we have in the textbook. This example involves the energy formula with Planck's constant H in it. So let's read the problem. It says a photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. What is the energy of a single UV photon and a mole of UV photons having a wavelength of 25 nanometers? Okay, so let's write down what we're looking for. Energy per photon. Okay, and we know that we have a mole of UV photons, having a wavelength of 25 nanometers. Okay, and let's see, what else do we know? Since we're using the energy formula, because it's talking about energy and wavelength, we know this, okay, Planck's constant times frequency. And then in our last example, we had a speed of light equals frequency times wavelength formula. So we could take this a step further and substitute frequency for speed of light and wavelength, because we're working with wavelength. So we need to have that in our formula. Okay, so first of all, we need to get our energy per photon. Okay, so I'm going to plug in what I know. Okay, so I know Planck's constant. Okay, so this is h. I know the speed of light. I'm going to use, again, 3 instead of 2.99. Okay, and then I know that I am dealing with wavelengths of 25 nanometers. Okay, so again, remember, wavelength can't be in nanometers. It's got to be in meters to have our units work together. So a nano is 10 to the negative ninth. So I'm going to take that out so that I'm just in meters. Okay, so now notice what happens to all our units. Okay, that is going to cancel and give us our joules. So multiplying on the calculator and dividing, I've come up with 7.96 times 10 to the negative 18th, and that's joules, okay, per photon. Okay, so that's our energy per photon, but now we want to know the energy for a mole of photons. Okay, so this is joules per photon, and we know a mole has 6.02 times 10 to the 23rd particles of anything. In this case, we're talking photons. So we just take it a step further so that we can figure out how much energy is in a mole's worth instead of just a photon. Okay, let the calculator do the work. Photons cancel. And I come up with 4.8 times 10 to the 6 joules per mole. Okay, so that's solving a problem with the energy formula. This is a second type of Planck's equation type problem. Reading it, it says the ionization energy is the energy required to move an electron from an atom in the gas phase. The ionization energy of gold is 890.1 kilojoules per mole. Is light with a wavelength of 225 nanometers capable of ionizing a gold atom? That means removing an electron in the gas phase. Okay, so we would solve this using Planck's equation. So let's write down everything we know. We know the ionization energy is 890.1 kilojoules per mole. We've got a wavelength of 225 nanometers, okay, and then is this wavelength capable of ionizing an electron from one atom? Okay, so let's find out how much energy it would take let's get the ionization energy for just one atom, okay, so let's see, kilojoules per 1 mole, or per mole. Okay, and then we know that in 1 mole, there's 6.02 times 10 to the 23rd atoms. Okay, so dividing that out, I end up with 1.48 times 10 to the negative 21st joules per atom. Okay, so now I'm per atom instead of per mole. Okay, so the equation looks like this. So we'll solve it for wavelength, because that's what we're trying to see, if this wavelength has got enough energy. And so wavelength equals hc over E. Okay, so I'm going to move this and plug in over here. So hc over E, I'm going to have 6.63 times 10 to the negative 34 joule seconds times the speed of light, meters per second, over the energy, 1.48 times 10 to the negative 21st joules per atom. And I'm going to let the calculator do the work. And now I end up with a wavelength of 1.344 times 10 to the negative 7 meters. Okay, now we're comparing this to 225 nanometers, so let's put this in nanometers too so we can compare them. So in 1 meter, there's 10 to the 9th nanometers. Okay, so multiplying that out, I end up with 134.4 nanometers. Okay, so 225 nanometers is it's too long. This is a longer wavelength than this, which means it has less energy in it, and so this wavelength would not be capable of ionizing an electron from an atom of gold. So no, 225 nanometers is too long, therefore too weak. Okay, so it has to be something shorter than this to ionize the electron, or at least be that. Okay, the photoelectric effect is one of those topics I was talking about that was having difficulty being explained with the idea if that light only acted as a wave. But now if we look at light as acting as a particle, we can explain this behavior. Okay, so here's a quick little video explaining what the photoelectric effect is.
The photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
Okay, and this was Einstein's area of expertise, and this is the idea that's behind those doors that we have at our grocery stores when we walk up and then they see us or seem to detect us, and the doors open. Is it's based on this photoelectric effect. So now we've been talking about uh, energy having that particle-like behavior, and now we've discovered that energy also has mass. And this is Einstein's equation equals mc squared. So we know that light has a dual nature, okay? We know that it acts like a particle and it acts like a wave. But I wonder then, is it possible for matter to have both wave and particle properties? And the answer is yes, it is possible. And a man named Louis de Broglie discovered this concept, and he put together Einstein's equation and Planck's equation, and he was able to figure out how to calculate the wave properties as well as the energy and the particle properties of matter. And so I'm going to insert a clip to show how to use de Broglie's mathematical relationship.
We were just discussing the idea that if light has a dual nature, then I wonder if matter has a dual nature. And Louis de Broglie is the scientist who supplied the answer to that. He put Einstein's energy with mass together with Planck's energy with wavelength. Well, this is frequency, but wavelength is tied into that. He put them together and showed that it's possible to calculate the wavelength for a particle. And so he took Einstein's work, and then there's Planck's work, and he put them together. He rearranged for wavelength, and he came out with Planck's constant divided by mass times the speed of light. And then if we use a particle with velocity not at the speed of light, so at some velocity, we can calculate the wavelength for that. And so here's a typical de Broglie equation type problem. Okay, so we're talking about a golf ball. So we're looking to see if we can calculate the wavelength of a golf ball driven with a velocity of 40 meters per second, and the mass of the golf ball is 10 grams. Okay, so if we use de Broglie's equation, wait, I don't want to write on that. If we use de Broglie's equation, okay, and plug in what we know, we know Planck's constant, we know the mass, and now the mass should be in kilograms to keep all our units consistent. Okay, so let's see, 10 grams is 0.010123 kilograms. Okay, and the velocity is 40 meters per second. Okay, and so now I'm going to let the calculator do this work, and I get 1.66 times 10 to the negative 33 meters. Okay, and so let's take it to nanometers, since that's what we're kind of used to working with wavelengths. Let's see. In 1 meter, there's 10 to the 9th nanometers. Okay, so that would give us 1.66 times 10 to the negative 24 nanometers. Okay, look at that number. It is so insignificant that we can't even detect a wave that small. So that's why we don't worry about wave properties for large objects, because you can't detect them. Okay, so there's our de Broglie wavelength type problem.
Okay, and so this is the end of this first podcast on the idea of atomic structure, and so we'll continue on in the next podcast.